Hello, everyone. My name is Robert Browning, and today we will be talking about of the two genres in this class. So we're dealing with the explainable AI and the generalization. Right? In this class, this paper falls into the explainable AI category, which will open that up a little bit. The paper's title here, as you can see, their method is RISE, which obviously potentially plays off of some of the older methods like LIME, for example, other black box methods that have done similar work. These guys are from Boston University, and this was an oral paper at BMVC 2018. So in general, the goal of this work is to tackle a problem that many of us have faced or asked at some point, and that question is essentially, for example, in the age-old question about mirrors and AI and things of that nature. But here we're looking at a picture of a lioness and her cub, and we have this reflection on the water, and so we end up with this classifier, and it's giving us a 94% assurance probability that we have a lion in this image. So our questions at this point become why or what in this image is leading our classifier to believe that there is in fact a lion in this picture. For example, obviously this is a lion, but is the lioness and the cub, are they both contributing to that probability, or is it one or the other? Or potentially, are these reflected regions contributing as well to the probability? So this work, what it does is create saliency maps to help us determine what regions in the image are contributing the strongest with this heat map here, or in other words, these important maps, to show us that this classifier was saying that we have a 94% chances of a lion in this image based solely on these regions here. Well, and I say solely with measuring importance as we work our way outside of the heat map. So we can see that this lion cub is not contributing to that decision whatsoever. So here, and by the way, this image contributes very little, but I really liked the picture. I thought it was funny. There's like this black dog, white dog, okay? But the point is this. So what is explainable AI? And so as I worked through this paper and I looked through all of it, and I realized we end up with these important maps that shows the regions that help to determine the probability scores that we received. And I felt like, okay, that gives me some level of explainability, but for some reason I also feel like I'm still missing something. I'm not getting maybe a reasoning, a true reasoning or intelligence, a sentience of why that's the case. And so after speaking with Dr. Bagci and uncovering the various methods, so what we're dealing with in this paper is what's called a perturbation method. In other words, we're going to perturb our inputs and measure the outputs. However, other methods of explainability also exist. Another one of those that's very familiar to all of us, and most of you, I'm sure when you start working in the field of deep learning, you go through tutorials where they show visualizations of the different filters. After layer 1, after layer 2, you can see how they move from lower level to higher level features. And you can see the visualization of these things. That's another area of explainability. And the last one, and clearly the most general form of explainable AI, is reasoning methods. Methods that truly explain the why and the how, the origin, every step of the way, at a much more semantic, higher level idea of what's happening here. So one thing I thought was interesting, and we haven't discussed this in this class and haven't seen it in any of the papers, but I read an article online that talked about the difference between interpretability and explainability, which could arguably be in the English language synonymous. However, they talked about the difference being in the case of interpretability, that's being able to discern the mechanics without necessarily knowing why. And I feel like this paper falls into that category, especially because there's so much emphasis on the black box approach here. We're able to perturb the inputs, we're able to measure the outputs, but we don't exactly know why it's doing these things, a cause and effect type of situation. And then there's a higher level explainability, and this falls into the reasoning category, being able to explain in human terms the inner mechanics of our system. So two potential categories, this potentially a subcategory of the latter. So in our case, what we're dealing with here is, for example, in this image, we can clearly see that we have two sheep. So sheep 1, sheep 2. In our classification probabilities, we have a sheep at 26%. So there's probably a sheep here depending on our threshold value. However, it's also reading that we have a cow. So it may be interesting to determine where is the reasoning for the sheep and where is the reasoning for the cow coming from. So by using these importance maps, we're able to have explanations for any category in our data set. So in this case, you can see the saliency map says, this is where I'm getting an idea of a sheep from. However, this looks a lot more like a cow to me. Another example of that would be these two eagles here. Well, I have 100% bird in my image. However, I'm also saying that 39%, there's a person somewhere in here. And so these saliency maps allow us to get a better idea of where those reasons are coming from. I think it's a little bit interesting here to look at both of the birds are contributing to the person class. So these saliency or importance maps can be used in various lines of research. The obvious case is what we've done so far, and that is in the case of image classification. And what's important about that is these saliency maps, you can see they change here as we perturb and average more and more masks. So we can choose that level of granularity that we want in the mask output. The importance here is that we're going to get, there's more than one fish in this picture. And that's important. So while we may categorize this as a goldfish, we can see with this heat map that there's more than one goldfish contributing to that prediction. You can also use this in a video level. However, for the video, it's again going to be computed on the frame level and then compiled to a video level. So in other words, we're not using the 3D convolutions here, which is something we maybe want to talk about later. But these same processes can be applied to a video level. Another interesting thing I think about, or that I thought from the paper, was the fact that we can use this for NLP type stuff, sentence generation, or for example, if we're asking a question, or it will highlight. So the point is that these saliency maps will highlight certain regions of the input. Well, in this case, the input was a word vector here, and it can highlight those for us and show us where the important regions are. So other methods exist in this type of work. I'm sure you've all seen one. This is very popular, the GradCam from CSAIL. These first models here focus particularly on what we'll call a white box model. So the white box model needs access to the gradients. It needs access to the weights and so these models are able to come up with these importance maps. However, they rely on the inside of what your model is doing. So if you think about in the context of a proprietary model, for example, Facebook or Google, who have these proprietary models that they don't wish for, because, for example, when they collect data from us, they say, this data will be used anonymously. Well, it's used anonymously to train their classifiers, etc. And so if we were to have access to that model, here's an input, find the output, we wouldn't be able to use these methods because they do rely on the inside of those models. Moreover, you could compute gradients, etc., if you had access to their loss function. However, without access to their loss function, which does prevent some level of adversarial attack, without access to their loss function, we won't be able to access those gradients along the way. So what this work does is employs a black box model, which is also not new. However, the results are much better than the other results, both qualitatively and quantitatively. When I look at the images, for example, with the line method, that's kind of that was the other major work before RISE came along. I just don't feel as motivated or as convinced after looking at some of those images. The heat maps to me are so much more important because this relies a lot on, you can see this segmentation here, and then it applies heat in those certain regions. Not as convincing to me. So what our method does, wrong direction. So what we do in our method is we have an input image, element-wise multiplication, and I'll talk more in depth about the actual process, but element-wise multiplication with a mask, a randomly generated mask, is input into the black box, and then we're getting a probability score out. So in other words, what is our prediction after we've input this into our model? So we continue this numerous times, and after we've done that, each one of these masks here, element-wise masked images, is multiplied by its probability score, and all of these are averaged out to produce the final saliency map here. So in a slightly more granular approach, what's happening is that we actually downsample our images. So we resize them to a much smaller image size. So let's say, for example, we're given a 224 by 224 image. We downsample that to, let's say, not even 128, but let's say 56 by 56, something small, okay? 50 by 50, for the sake of argument. What we do then is we generate binary masks for that smaller image. So we're going to insert zeros and ones randomly, and we're going to create thousands of these. And we're going to take those images, we're going to take those frames, those masks, we're going to upsample those masks larger than the original image size of 224 by 224. And then we're going to randomly crop out 224 by 224 from that mask. So here, what this is telling us, and I didn't include a lot of the math from the paper because personally, I didn't feel like there was a lot of value added. To me, the math from the paper contributed in an after-the-fact sense. For example, we developed a method. It's very intuitive and simple. It works. Here's why we think it works. And that's where they went through the entire expectation formula. If we have time, we can go through that. But the point is that after upsampling these binary masks, the values in each one of those pixels is no longer 0 or 1, but somewhere between 0 and 1. That's why we get these fuzzy or these continuous masks here that are applied over the image. Moreover, after creating thousands and thousands of masks, putting them through our network, we're actually going to use random sampling or Monte Carlo sampling to sample those so that we don't actually have to use all of them to save on time constraints. So here you can see that the level of the importance maps that you wish to achieve, good, bad, could be, is a granular process itself in the sense that how many masks did we generate and what was our threshold for the Monte Carlo sampling? Did we want more masks? Did we want less masks, etc.? Okay. So this is just a little bit kind of more illustration on the whole process. So we take those smaller binary masks, we upsample them to a larger size than the original image, and then we randomly crop out from that the size of the image itself, the original image. So another benefit of these masks, for example, are that sometimes as human annotators, we may see something in an image and we may believe that that contributes to the salient region or the important region for why the algorithm is predicting certain things. However, these maps allow us to realize that those things are not always the case. And so one of the metrics designed in the paper is called the pointing game. So they developed a total of they have three metrics: deletion, insertion, and the pointing game. The third metric is the pointing game. And what they say is that given an image, let's say, for example, that a human annotator put a bounding box around this region. That's what I think contributes to the prediction. And then they use their saliency masks here to say, this is actually what the machine was using for that prediction. If the most salient region, so let's say for sake of argument that this wasn't the most salient region, let's say here was the hottest point on that map, and it was outside of the human annotated bounding box, we would call that a miss. However, if the hottest region was inside of that bounding box, let's say here, we would call that a hit. The pointing game score is calculated by hits divided by hits plus misses, or total, if you will. So that score was calculated there. Again, you can see, as a human, I would say this entire stadium arena area here contributes to the decision However, you can see these smaller regions here are what is truly contributing to the overall prediction. So here's a little bit of a illustration of the deletion metric that they developed. So for example, this elephant is called a tusker. And in this, they developed the saliency map, the importance map, and you can see that this region here is contributing the strongest to the prediction that we have. So here what they're going to do, instead of blurring this region, instead of removing it entirely, they found that the best method was to set these to a fixed constant value and replace those values as we began to delete. So the way you can look at this is with a single object as far as implementation is concerned, if you wanted to implement this in your own personal work. So say we were given this saliency map minus the elephant in the back. What you could do is you could order as an array, you could flatten that array, you could order that array from largest to smallest. And then what we have to determine is how many elements do we wish to delete per cycle. So let's say we wish to delete capital N pixels at every iteration. So what we would do is we would start to delete these pixels here because as we had flattened the array, these pixels would find themselves at the very beginning. And so as we delete capital N at each stage, at each threshold here, of course this being some level of discrete, we begin to delete the regions which are most important to least important. Next we have the insertion. So while these methods are complementary, deletion and insertion, you can see that they're not true opposites of each other. So for example, here the background is not that single constant gray. You can see what we've done is blurred the image overall, and then we began to reinsert the most salient pixels into the image as they found their way in the array. So going back to this deletion, you can see here the point of this metric is this. So as we begin to delete, you can see on the x-axis here, we have percentage removed, so total pixels removed as a percentage. And here on the y-axis, we have the prediction score, okay? So here, you can see as we begin, so in the very beginning, of course, it was predicting at about 80% that we had an elephant. But as we begin to remove this most salient region, this is where the idea of the area under the curve comes in. We can see that the area under the curve, and particularly the curve itself, is moving closer to a prediction score of 0. Similar in the insertion, however, in the opposite direction. As we begin to introduce the most salient regions, you can see that has a huge spike here. But as we begin to put in these lower level, less contributing pixels, you can see that the AUC score is not changing as much here. So in a quantitative presentation of what we're looking at here, so the two causal metrics that we just discussed are both deletion and insertion. They trained two models, ResNet 50 and VGG 16. If I'm not mistaken, for VGG 16, I think they used 4,000 of the filters. They sampled a total of 4,000, and for ResNet 50, they sampled a total of 7,000 filters. You can see here in our deletion, lower is better. So in other words, without going back to the last slide and explaining it all over again, because maybe you didn't catch it all, but the point is the lower the number, the better. So you can see here we outperform the other methods. For example, this is very popular from 2015, the line method, as well as sliding window, which are both white box approaches. And in the case of insertion, the higher the better. So that's what we're looking for here. We outperform on those metrics all of the other prominent methods that are being used. For the pointing game metric that we discussed, you can see here that we're not actually outperforming all others. So for example, here you can see our method is the rise here. It outperforms on the case of the VGG, however, it does not outperform in the case of the CAM. The drawback of the grad CAM, though, is that it requires access to the inside of your algorithm, which you may not always have access to. So with that being said, you can see these results are very comparable to these in lieu of having access to the inside of your model. And that's it. Yeah. Questions? Please.
How if you wanted to fine tune your model after looking at these settings and maps, how would you think that could be done, or even just the deletion and insertion?
It's a great question. It's actually something I was thinking about too. For example, by using those deletion and insertion metrics and potentially even the pointing game, which to me seemed a little bit less. For example, if you look at this here, you can see that in the case of the pointing game, if I was an Amazon Turk, for example, and I annotated this entire region and said this is what contributes, and then the machine says this contributes, well, they both actually do lie in the same region. So to me, in some ways, this is a kind of a failure case towards the pointing game metric. So if we were to only use deletion and insertion, one of the things I was thinking about is by using those metrics, we create the saliency maps, and we use those potentially as some type of like segmentation labels or annotations, and then measure against the deletion and the insertion metrics to do a further round of, for example, if we found that inside of a certain region, like the hottest region was here, then maybe we should only train on that and see if we get different results instead of, or for example, blurring the image at certain levels. I don't have a good answer other than that.
Would the complexity of the deletion insertion become infeasible to do that way?
I suppose it could be if you were retraining. Praveen, do you want to ask your pre-processing question? I feel like it leads into that. You do.
Yeah, you know the question.
Oh, okay. So Praveen's question was, yeah. So Praveen asked beforehand, for example, so if I may, I'm going to show you their demo website. So for example, on their demo website, you can get a little bit of a better idea here, what we're working with. So say, for example, we chose this image, right? So on their demo, you can actually scroll through and you can look at the saliency importance maps here. It's very nice project page here. So let's say we were to click on this, and then we wanted to look at, so here we have the rise method, here we have the line method, and here we have the grad cam on the bottom, which we can't see entirely. Let's move this up a little bit. So for example, as we scroll this little UI bar, you can start to see the deletion and the insertion. So those are nice, maybe at illustrating, in general, illustrating the concept further. However, Praveen's question was, and more importantly, came from as he does super resolution, is that this image here, we felt like this image here could have actually been classified using the classifier itself. In particular, a lot of the times, one of the methods employed could be in pre-processing, could be to blur the image itself and train on that as form of like a data augmentation. So if a black box method, if this is truly a black box approach, then if someone had trained their classifier on images that look like this, it could potentially perturb our methods, our metrics, and the deletion and the insertion. And